Good morning. I'm going to cover the ideas that we find in chapter 24 today. It's about matched or block paired data. So, what you're looking for when you're dealing with this type of data, most often it's before or after. However, it could be two different people matched together. The textbook talks about speed skating races, and they're trying to see if pairs who go up against each other, if somebody who starts in the inner lane or outer lane has an advantage. So then those two skaters would be paired. It could also be something like if you're trying to test running shoes, one person would test both shoes, so do both treatments, and therefore become a matched pair to see if there's a difference in time, for instance, when they run in one pair of shoes or another. So this one here is about resting pulse rate. And so what this one is they're trying to see if this exercise can reduce resting pulse rate. So they're going to have to measure somebody's resting pulse rate prior to using the machine or device and then after. So when people become a before and after, you would look at matched pairs. So as I take a look at this one, the first thing I did was I made sure that I have a third column. I've got Alan's measurement of his resting pulse rate before, his resting rate after using the machine, which was 3 times a week for 20 minutes. So that was the treatment he was dealing with. And the last column becomes what happened to his resting pulse rate. So for Alan, the difference was 0. For Brandon, within context, Brandon's pulse rate went down by 4. So that's why it's represented as a -4. You need to really consider context here when you're looking at it. We're looking at pulse rate to go down. So we want to represent all of those with negatives. Don't try to memorize whether you do 79 minus 83 or 83 minus 79. Think about the context of the problem and just be consistent with it. So once we decide we've got paired data, all we have to do is make that third column, which we will represent as the difference, okay? Because that's going to become part of our notation when we're writing things out. So we represent that as the difference. That's all we need in our calculator is that one list. So I have a list here. I'm going to put it into my calculator, which I've already done here at list 1. And then with that list 1, now I can run a t-test. It becomes a very simple t-test, just like we did in chapter 22, run off one list of the differences. So before I do that, I'm going to go ahead and write out my hypothesis. Okay. So if I take my hypothesis that, remember, the null hypothesis is always no change, okay? No change, no disease. So what I would do is write out for this one, H sub 0, okay, the null hypothesis, mu D equals 0. So there's no change in pulse rate for participants. Now, in order to write the next part, I need to make sure that I look at the context of the problem. So going back to the context of the problem, right here it asks, is there evidence that this kind of exercise can reduce resting pulse rates? With that in mind, I'm going to go ahead and write my alternative as mu D less than 0. Okay. The exercise reduces pulse rate. Okay, so once I've done that, I've done the P and the H of phantom. Now I head into the conditions that I need to check. Okay, so for this one, you need to actually state that it's paired data, and you have to then check the other things for a t-test, and that would be that we have independence and that our differences are normal or approximately normal. So I'm going to say specifically, the data is paired. Each man is tested before and after. Okay, or each pulse rate is taken before and after from the same man, something like that, that indicates that you know you have paired data. The next part is the subjects are independent. Now, we can't say that this is random, okay, unless we're told it's random. And since it looks like it was some sort of participation, well, it's not a random sample. So we've got volunteers. And again, there's no indication of randomness here. So what we're going to need to check for this one is that it's less than 10% of the population. Okay. So we can say 10 participants. Oops. Are less than 10% of all men. And we're going to have to say, we assume they are representative. Representative. Oops. Lastly, I need to make sure that I check a histogram of the differences. Okay, so I'm going to go back to my calculator and I'm going to make sure I turn this plot on. It is L1 that I'm looking at. So I'm just going to go zoom 9. And there I've got relative symmetry here. So I'm going to make sure that I've done that right again because it looks like the one I used the other day. So plot 1 on, zoom 9. Yep. So we've got right there, we're going to copy that histogram best we can. Okay. So when I look at that histogram, it looks something like this. Okay. So I'm going to say histogram of differences is relatively or approximately normal. Don't say it's normal, say it's approximately or relatively normal. Okay, so this meets normality condition. Okay, so once again, you need paired data. You need less than 10% of the population or random allocation, random sample. And you need to make sure that the histogram of your differences is relatively symmetric so we can assume normality. Now we're going to name the test. Okay, so we can say that conditions are met. We're going to do a 1 sample t-test for paired data. and it's going to be one tail lower, okay, at 9 degrees of freedom. Okay, remember that's n minus 1. Once I've done that, I'll go back to my calculator, okay, move over to stat test. Oops, I chose a z-test, so back over here, move over to stat test. Number 2, we're using data. We need to change our null mean to 0, that there's no difference. It is list 1. We're going to move to less than. And so let's go ahead and calculate first. So what I have from my calculations, you can see that I've got a t-score of negative 3.5, so my p-value is 0.003. My average difference was negative 2.8, and my standard deviation was 2.53. Okay, so I'm going to get all of that into writing down for my formula here. So we're going to go critical t-score at 9 degrees of freedom equals our average difference is negative 2.8 minus our null, which was 0, over 2.53 divided by the square root 10, our sample size. That was negative 3.5 was our t-score. Okay, so we know we're going to end up with a p-value that's very small. Headed back to our calculator, let's just go ahead and look at the drawing of this. Oops, didn't mean to leave that histogram there. But you can see, if I look at it, that I have my t-score right there. I've got my p-value of 0.0034. Okay, so as I draw that out, I've got negative 3.5 right here. Even though we couldn't see it on the calculator, that means my p-value, this space right here, is 0.0034. Okay, so in order to write that in notation, okay, I'm going to do the probability that t is less than negative 3.5 equals my p-value of 0.0034. Okay, so in this case, we are going to reject the null. Okay, we do have evidence that this device lowers pulse rate. Okay, so just to give you some notation, if I were to write the mean here, I'm going to write d bar. Okay, this is going to be mu d. Down here is the standard deviation of d bar. Okay, so if you see that d bar, you know you're dealing with a paired sample. So I'm going to go ahead and write my conclusion. With a p-value so low, we reject the null. There is evidence, there is strong evidence that the device lowers or reduces pulse rate. Okay, so that takes you through the whole process. If you need any more help, there's another example on PowerSchool. You'll see a picture of it. And I'm going to put the key for the problem set on as well by later today.